Just a quick announcement. So tomorrow we have lightning talks before lunch, 5-minute slots. Come up and talk about anything related if you want. I've just added no, I haven't done Git push yet, but there will be a link on the website in about as long as it takes GitHub to stage the page. And so a few minutes, and if you want to present a lightning talk tomorrow, we have slots. So yeah, and 5 minutes, one slide, that'll do. Cool, all right? Neil is up next. So between talks, Carl, I guess you're going to give us a thumbs up when we're good to go?
Yeah.
Okay, cool, all right. So presenters, please wait for Carl.
Sorry. Thank you. This is was a very well set up presentation, and the questions and Alexi's presentation. And I want to say it's an honor to be here, especially to be presenting with Alexi. I really respect the work that he's done. So yes, I'll be talking about a tool called Netlistsvg, or how to draw a better schematic than Graphviz. Funnily enough, this presentation is also an observable HQ. So it's all trendy right now. So a little bit about me. My name is Neil Turley. I'm from Austin, Texas. Netlistsvg is a personal project of mine. I work as a software engineer at National Instruments. Mostly I work with our Compact Rio product line. Even though I'm a software engineer, I work a lot with supporting our hardware products. So first I want to talk about what is a schematic or netlist and why would you want to draw one. So a netlist is just a collection of cells or nodes or components, and then a list of the connections between them. So the connections are sometimes called nets, wires, or edges. I use those terms interchangeably. And the idea behind drawing them is to match your mental model of what you think you're designing and what you are actually designing, what the tools think that you are designing, and to make sure those are the same thing. Which is important for pedagogy if you are first learning digital logic for the first time, or you're learning a new language to be able to design digital hardware. It's also important for debugging to make sure the tool is doing what you expect it to do, as well as documentation so that you can communicate to other people about what it is that you created. So it's not a universally agreed upon criteria of what makes a well-drawn schematic. But some of the general rules is that the cells should be spaced out and not overlapping or on top of each other. Related cells should be close together. In other words, the wire length should be as minimal as possible without causing overlap. And there should also be minimal number of crossings and minimal number of wire bends. And so this is an example of a pretty well-drawn schematic by this criteria, in that the related components are close together and there's not too many bends or crossings. So there's a related field in drawing schematics, which is traditional mathematical graphs. So the traditional mathematical graphs have a lot of very similar properties, in that you have nodes and you have edges that connect those nodes together. However, schematics have some additional properties that make them a little bit different. For instance, the fact that we care about the ports of which port is connected to on the cell, as also in traditional graphs you only care about the one edge connector connection. However, in schematics usually you'll have many things connected together on a single edge, or a hyperedge as they're called. We also have symbols that we care about, so just circles usually isn't ideal, and we have conventions for orthogonal routing, that is just wires going vertical and horizontal, and we also have conventions for where there should be feedback and where should be going left to right or top to bottom, for example. So there's many graph layout algorithms that exist both in academic literature and out in the wild by different tools that draw schematics. Some of the different algorithms that people choose to use are force-based. Those are fun. Simulated annealing is another one where it tries to randomly place things and then tries to see if it can scoot them to make it better by that metrics that I mentioned. There's also a layered approach. Sometimes it's also called Sugiyama method. And there's also the simplex algorithm, which is basically treating it like a constraint optimization problem and then trying to find the solution. Basically, since we have a pretty mathematical criteria of what is a good schematic versus a bad one, then we're just trying to find the solution space. We're trying to find what all the values of the variables should be such that we get the optimal result. So this is a force-based example of a force-based layout. It's basically equivalent to hill climbing in that it's trying to find a better algorithm than the current position, so it has state behind it. The nice thing about force diagrams, they're super fun. They're always a crowd pleaser. So you can grab things and you can see like, ooh, it moves around. It's very, very fun. The idea behind force-based layout is that part of what makes them visually pleasing is it's very similar to the way the physical world works. And so the edges in this case, we create a spring-like force that pulls them close together. And then the cells have electrical-like charge where they want to spread themselves apart. And so as a result, it reacts and they produce some of the attributes in that the cells will be spread out, but the related cells will be close together. And so it can make a schematic that's very close to ideal. So the reason why I kind of got into this game of trying to draw schematics programmatically was Clifford Wolf, the author of Yosys. He actually made a GSOC project. I don't know, this is several years ago. And I read about it and I thought, that sounds great. And so I decided to try to compete with the intern. So in parallel to this intern trying to solve this problem, I was trying to solve it. And he didn't know, I'm sure he never even knew my name, or probably still doesn't. But I was competing with him and I was following everything he was doing and trying to do a better job. Luckily, I won by default because he dropped out halfway through the summer. And then actually the next year, another intern also made an attempt. And so so I had a competition going between them. Some of my first experiments, I tried to use this force-based layout because I thought they looked so cool and snazzy. And so here is my first attempt. It is cool. It wobbles like jello, and it jiggles, and it kind of oozes around, and you can drag it around. This was attempt number 1. So it oozes slowly, but the cells are draggable, which is fun. The next attempt was this one. So this was using D3, which Alexei mentioned briefly. D3 has a library to do forces. And so rather than doing my own forces and emulating all these different like springs and stuff, I had D3 do it. I didn't spend as much time trying to style the cells to use the correct symbols. And I gave it a much more challenging schematic to see if it could draw. One of the things you notice that's really common for force-based layouts is it tends to find a stable equilibrium in a circle. And so all of these things are all wrapping around here. And also when it has feedback, so it's wrapping itself around, it ties itself into a knot. And so it gets really compact, and that's causing this big mess right there in the middle. But the nice thing, because it's draggable, you can fix it up afterward. So a human being can, at least it gives you somewhere to start with. I get scared every time I click that back button now. Okay, so that was attempt number 2. And that was, I learned a lot from that. I spent a lot of time trying to tune forces. And to address some of the problems with like feedback, for example, I started trying to learn about the layered graph techniques. So I started reading about how Graphviz does its layout. I started learning about how to do like dummy node insertion, which I'll be talking about in a second. And so then I ended up with this one, which was one of my more impressive ones. This one I actually used yosys.js, so this is actually a Verilog design. And then it completes synthesis and draws it and ends up with that, which is pretty good. This is still force-based. If you noticed it, it sprang out from the center. And the forces are still acting, so I can actually move things and then pin them into a position. And the graph, all the forces try to adjust around the constraints that I've now placed on the position. And I can unpin them, and then they go back into place. So this works pretty well. One of the problems with this is the fact that I had to spend a lot of time tuning the forces to produce, and I was looking at this example the entire time, and so all the forces are fine-tuned for this particular schematic. There's a simpler example here that it doesn't do quite as good of a job. Now things are overlapping, like that's on top of that, and so I'd have to go fiddle with the forces again if I wanted this one to look as good as the last one. But still, it was very, very good for what I had. So I want to talk about this. I said that I was using some of these layered graph techniques, and so I want to talk about this layered graph layout or Sugiyama layout. There's many academic papers that talk about these techniques. One of them is Sugiyama, Gansner, and they break down the problem into these steps. And the first step is to break cycles, then they do rank assignment, insertion of dummy nodes, reordering columns, and then assigning edge channels. All of the implementations have slight variations in these, but usually that's the main structure of all of the implementations of this. So first is cycle breaking. So a rank is, in our case, is a column, and so we would like it to act like a directed acyclical graph. However, it's common for graphs to have feedback, and so we need to tag particular edges to be backward or reversed. And depending on which one we tag, we'll end up with a different vertical or horizontal position for these nodes. They'll be in different ranks. So if I pick this one, then it ends up being in this order. This one's this order, and so on. And so we need to identify which are the feedback edges, and we need to tag those as reversed. Then we need to do a rank assignment. So rank assignment is an interesting problem. The first thing we usually start with is called longest path. And the way we do that is we start out, we traverse our now directed acyclical graph starting from the root nodes, and we go to the right, and we enforce that all of the nodes that we're connected to, that we're driving, to be to the right of us. And then we push them over until we get to the leaf nodes, and then we go in reverse. So we start with the leaf nodes, and then we make sure that everyone that is driving that particular cell is to the left of us, but as close as possible. The result of this algorithm is that every single node is as far to the right as possible, except for the leaf nodes, which are as far to the left as possible, without violating the fact that any of the edges are going backward. So in the blue, you can see the algorithm is going forwards to the right, and it's pushing all of the child nodes, all the things that it's driving, to the right. And then the red is when we're going from the right to left, and then we make sure that all of them are in the correct position. Sometimes they follow this up with something called network simplex, which means that instead of all being crowded to the right side of the graph, it more equally distributes them. I won't talk too much about that, partly because it's complicated and partly because I'm not 100% convinced that it produces better schematics. But that's very common. The next step is dummy node insertion. Sometimes dummy nodes are called virtual nodes. And so to simplify the problem, every single edge that crosses more than one column, we insert nodes so that it no longer does. So in this bottom case, this node and this node, we need to insert a virtual node there. And if it's a reversed edge, we also need to insert an additional 2 nodes so that it can change direction and go backwards. So this is a reversed edge, so we need to insert 2 virtual nodes there. So now, after we're done with this, then now we only need to worry about edges going between adjacent ranks. Does that make sense? Then we do node ordering. This is where we're trying to find the relative vertical positioning of the nodes within each column. And so the way we do that is that we go from left to right, and we go sort the nodes by the relative positioning of its neighbors. So first we just consider my neighbors on my right side. So AB stay in the same, oh, I did this way. AB stay constant here, and then I sort CDE so that they're sorted with respect to AB. And then I sort FG with respect to the middle 3, and I go the other direction, is that I sort CDE with respect to FG and then AB with respect to CDE. It's not clear exactly how many times you need to go back and forth to reach a good, stable point. But yes, in general, the point of this is we're trying to reduce the edge crossings. Even when this operates many times, you'll still have many edge crossings due to the nature of this algorithm. If you do use the median, there's a bounded number of edge crossings. But still, I'm very dissatisfied in many cases with the number of edge crossings that this algorithm sometimes causes. And then the last step that I want to talk about is the edge channel assignment. So in the spaces between the nodes, between those two ranks, you need to decide where the vertical lines need to be. So you can't have unrelated nets on top of each other, and you want to find the ordering of those vertical lines so that you have the fewest number of crossings. So in this case, the minimum number is 1 if you assign the channels in this particular order. Good. So that is some of the techniques in layered graph layout. So I had a plan to go write this whole layout engine that was purely using layered layout. And then I found out that University of Kiel had beat me to it and written a really useful tool called Clay at the time. More recently, it was adopted into the Eclipse Foundation because it's being used by Eclipse to do like their UML diagrams or something. It was originally written in Java, but they transpiled it to JavaScript, so there's a JavaScript version of it. And you'll notice that it is capable of diagrams with very similar properties to digital schematics. That these, in their example here, you can see they have ports, they have hyperedges. It's very complete and very good at doing the kind of diagrams that digital schematics are similar to. And so I took elk.js, and then I decided as an input format to use yosys JSON, and then I decided to make a skin file format. I was inspired by Wavedrom, actually, because I wanted to decouple the actually how to draw, like what it should look like, from the actual layout algorithm itself. And so the skin file decides what each of the template nodes should look like, and then the netlist decides what there actually is to be connected together. And then I go past that to elk, which also takes JSON conveniently, and then I produce a SVG result. There's a lot of like reformatting the data because all of these file formats are very different in how they're organized, but all of the hard work is mostly being done by elk, which is the layout part. So here's a fun little like live example. So this is Verilog here, and this is the diagram that it generates with Netlistsvg. The fun part is because it's live, I can actually like change it and like, look, there's feedback. When I show this to people that are used to using Vivado, their mind blows, like you just synthesized in a browser. But it's fun, and you can even, like very quickly, you can start to give it weird things to see like, what happens if I start doing like that, or like that, and like, oh, that's what that weird Verilog means. You wouldn't see that, but now you very quickly can align your your text representation into a mental model that, oh, that's what it's talking about. Also recently, there's been an interest in text-based languages for board-level hardware, like analog schematics with resistors and capacitors and so on. Analog schematics have some very different properties than digital schematics, which makes them quite challenging. Elk is not ideal because of some of these. For instance, analog schematics have a horizontal flow as well as a vertical flow. And analog lets don't necessarily have a direction, whereas digital schematics, there's a driver, and then there's people that are like reading that signal. And the analog components also can be rotated, and digital schematics, thankfully, have an orientation. But we did our best to try to make Netlistsvg be able to do analog schematics, and in some cases it does a passable job. And so, for instance, here's an example that it did an okay job. There's still some visual artifacts, but it does a pretty good job. The analog schematic does a purely vertical flow, so the thing it falls down on the worst is anytime there's horizontal connections between components. It also does a poor job when there's lots of different things connected to the same net. So here, it's not sure who is the driver and what direction the line should go in, and so it does a pretty poor job there. But overall, it does acceptable for simple schematics. So my future plans for Netlistsvg is to make it more useful and easier to use for a lot of things you might use it for. Currently, we don't support hierarchical designs, even though Elk is totally capable of laying those out. I also don't have net labels yet. I also want to make it so you can highlight nets because sometimes it's hard to follow the lines, and so if you could like mouse over and follow them, that would be much easier. And I also am hoping to do some post-layout interactivity. For right now, I mostly was interested in the command line interface like usage of generating a static image, but sometimes you want to manipulate it afterward, maybe because it did a poor job and you want to fix it up. Because the earlier examples, you could drag the things around, and now it's a static image, you can't do that. And so I'm hoping to add that as well. And also my big plan in the long term is I'm hoping to write my own layout engine that just uses constraint optimization so that I can handle some of the tougher like analog schematic cases where I can do rotations in any kind of directions and that you want. And so I've been experimenting with that. I have a Jupyter notebook here where I was doing some like early experimentation to see if it was like going to work, if it was feasible, and the results are pretty good. Like it looks like it is able to do it in a reasonable amount of time, and it's producing pretty good results. It's taking too long to load, but yeah. So overall, it's looking pretty good. So hopefully someday I'll finish that, and I'll be able to handle even really terrible netlists and find a really good solution for those. And so that's all I have. Well, thank you.
Thank you, Neil. Questions? Yeah.
So when you have your algorithms generate a particular representation, you can look at it and say, well, this is better than the previous one. Do you have a metric to actually just evaluate automatically what the quality of the accomplished result is?
So not really. So as I said, there is some criteria that I have decided on, like the number of edge crossings and how close nodes are to the things they're connected to. However, Netlistsvg currently, layout's not my problem anymore, and so I can't change how it lays out even if I wanted to, and so it's just, I look at it and say, that looks really ugly. Once I have my own, if I ever do finish having my own layout engine, then there will be an actual function, a metric that I need to optimize, but I don't have that yet.
So very cool drawings. One question I have, I saw in your final thing you were saying that you plan to do hierarchical.
Mm-hmm.
And one of my concerns when I've been trying some of those things, when you try very big designs, they start to be unmanageable. Unless there is some hierarchical or something. What is your time frame, or what do you plan to do there? More automatic, or do you think by hierarchical is nice to have a module that shows like a box?
Yes, so in my mind, I haven't done it yet, but in my mind, I think in a hierarchical design, there would be an attribute on particular modules that you want to either be collapsed or to be invisible, because you may not want to see your entire design, but right now, this is just purely theoretical because I haven't done it yet. So.
And do you have a time frame to work on hierarchical?
I expect I will have some version of hierarchy working in the next few months.
Okay, great.
Anyone else? No, cool. Oh, Olaf.
So this is all really cool. Where can we find these things?
Sorry. So Netlistsvg is on npm, so you can just npm install it. You can also you can go to it on GitHub. So it's github/nturley/netlistsvg. Yeah. If you Google Netlistsvg, you'll find it pretty quickly.
I think the link is on the schedule, actually.
Good.
Yeah, on the bio. Cool. Alrighty. Thank you very much, Neil. That was good.